Hello student, myself Rajinder Kumar, lecturer civil at Government Polytechnic College, Amritsar. Today I am going to deliver a lecture on subject RCC design. The topic of my lecture is design of doubly reinforced beam with limit state method. So dear student, beam is any structural member which adjusts load mainly by bending, therefore it is also called a flexural member. It is generally of a rectangular shape. Now question is, what is the doubly reinforced beam? The RCC beam in which steel is provided in tension zone, that is below neutral axis, as well as in compression zone, that is above neutral axis, are called doubly reinforced beam. So beam in which reinforcement is provided in tensile zone as well as in compression zone is called doubly reinforced beam. Students, let me explain the concept of doubly reinforced beam with the help of diagram. This is the longitudinal section of the beam and this is the cross section of beam. This is the neutral axis. Neutral axis is the layer or lamina where there is no stress or zero stress. The zone lying above the neutral axis is called compression zone. And the zone lying below the is called tensile zone. The reinforcement provided in a tensile zone is called tensile reinforcement. And it is denoted by Ast. The reinforcement provided in the compression zone is called compression reinforcement, and it is compression reinforcement is denoted by Asc. So when the reinforcement is provided in tensile zone only, then that type of beam is called singly reinforced beam. When steel is provided in compression zone, when the reinforcement provided in tensile zone as well as in compression zone is called doubly reinforced beam. So the RCC beam in which steel is provided in tensile zone as well as in compression zone are called doubly reinforced beam. When the external load increased, which cause the greater bending moment, to resist the more bending moment, the moment of resistance is to be increased. So when there is more load on the beam, that cause more bending moment. To stabilize the structure, we have to increase the moment of resistance. There are two ways to increase the moment of resistance. So first method is by increasing the size of beam. So the moment of resistance of the section is directly proportional to the size of the beam. When we increase the size of beam, the moment of resistance of the beam section is increased. Second, by increasing the tensile reinforcement. So the moment of resistance is also depend upon the area of tensile reinforcement. As we increase the area of tensile reinforcement, the moment of resistance of the beam section will increase. So, if we use the first method that we increase the size of beam, then the oversized beam does not look well. Sometime due to headroom constraint, the size of beam is restricted. So, the drawback of the first method is the oversized beam does not look well, and there are sometimes there are problems of headroom and space or appearance. The second method, the over reinforced section are uneconomical, and the failure of these beam are brittle failure. So, when we increase the area of tensile reinforcement, the section become uneconomical, and these type of section fail due to concrete failure, and concrete failure is brittle failure. Therefore, there are no sufficient warning sign before the final collapse. Therefore, it is better to use the doubly reinforced beam. Next topic is the necessity of doubly reinforced sections. What are the various necessity of doubly reinforced beam, or under what circumstances doubly reinforced beam is required? First one is the when the size of beam is restricted due to requirement of headroom, space, appearance, etc., and the moment of resistance of the singly reinforced section is less than the bending moment caused by the external load. So, when there is the problem of headroom, space, appearance, there is more load, and we prefer to use doubly reinforced beam. Second necessity of doubly reinforced beam is when the beam is continuous over number of support, the section of beam at the support generally designed as the doubly reinforced beam. In the case of continuous beam, the doubly reinforced beam is required. Third reason, doubly reinforced beam is provided to reduce the deflection or to increase the stiffness of the section. To reduce the deflection or to increase the stiffness of the beam section, there is necessity to use doubly reinforced beam. Fourth one, when the load are eccentric, when the external load are eccentric, not centric, in that cases doubly reinforced beam is required. Fifth one, when the beam is subjected to accidental or sudden lateral load. So, when there is impact load is there, sudden load is there, in that cases we prefer doubly reinforced beam. So, these are the necessity of doubly reinforced beam section. Depth of neutral axis. The normal distance from the top edge of the beam to the neutral axis is called depth of neutral axis. This is neutral axis. Neutral axis is a layer or lamina in a beam where there is no stress or zero stress. The normal distance from the top edge of the beam to the neutral axis is called depth of neutral axis, and it is denoted by XU. The distance from the top edge of the beam to the neutral axis is called depth of neutral axis. The depth of neutral axis of doubly reinforced beam is obtained by equating the total compression and total tension. So, total compression is C1 plus C2, where C1 is the compressive force carried by the concrete area, and C2 is the compressive force carried by the compression steel, and C1 is equal to 0.36 FCK BXU, and C2 the compressive force carried by the compression steel is equal to FSC ASC FCC into ASC. So, C1 the compressive force carried by the concrete area is equal to 0.36 FCK, where FCK is the characteristic strength of the concrete, B is the width of beam, XU is the depth of neutral axis. C2 is equal to FSC into ASC minus FCC into ASC, where FSC is the stress in compression steel and ASC is the area of compression steel, FCC is the stress in concrete at steel level. Total tension T is equal to 0.87 Fy Ast. Dear student, let me explain the depth of neutral axis with the help of diagram. This is the beam section, this is the neutral axis, and the zone lying above the neutral axis is called compression zone. This is the compression steel, and the area of compression steel is denoted by ASC. This is the tensile zone, and the reinforcement provided in tensile zone is called tensile reinforcement, and it is denoted by AST. This is the effective depth of the beam, the distance from the top edge of the beam to the center of tensile reinforcement. It is called effective depth of the beam, and it is denoted by small d. This is d dash is the effective cover for compression reinforcement. So, this is stress diagram. Here C1 is the compressive force carried by the concrete area, C2 is the compressive force carried by the compression steel. So, this C1 is act at distance 0.42 XU, 0.42 XU from the top edge of the beam. C2 act at the distance at the center of compression reinforcement. So, this act at distance d dash. This distance from the top edge of the beam to the center of compression reinforcement, C2 act at distance C2. T is the total tensile force, and this is equal to 0.87 Fy Ast, where Fy is the characteristic tensile strength of steel, Ast is the area of tensile reinforcement. So, the lever arm for C1 is d minus 0.42 XU, and C2 act at distance d dash from the top edge. So, by equating total compression and total tension, we get total compression is equal to 0.36 FCK BXU plus FSC minus FCC into ASC is equal to 0.87 Fy Ast. So, from this equation we can calculate the depth of neutral axis. This will come 0.87 Fy Ast minus FSC minus FCC into ASC divided by 0.36 FCK B, where XU is the depth of neutral axis, Fy is the characteristic tensile strength of steel, Ast is the area of tensile reinforcement, FSC is the stress in compression steel, FCC is the stress in concrete at steel level, ASC is the area of concrete, FCK is the characteristics compressive strength of concrete, and B is the width of beam. So, now FCC is very small and neglected, that is loss, FCC is the loss of concrete area due to steel, that is very small. So, neglect FCC, then we get the depth of neutral axis 0.87 Fy Ast minus FSC into ASC, where FCC become 0 and divide by 0.36 FCK into B. So, this is depth of neutral axis. Next topic is moment of resistance. So, moment of resistance, first MU limiting moment of resistance C1 into lever arm. So, C1 is equal to 0.36 FCK BXU into lever arm for C1 is D minus 0.42 XU. This is the C1 and lever arm for this C1 is equal to this, and this is equal to D minus 0.42 XU. So, lever arm for C1 is equal to D minus 0.42 XU. So, multiplying these two we get the limiting value of moment of resistance. Mu2 is equal to moment of resistance developed by the compression steel. This is equal to C2 into lever arm. So, lever arm C2 is equal to FSC, as I told you earlier, into FSC into ASC minus FCC into ASC into D minus D dash. So, this is C2 and C2 lever arm for this is D minus D dash, total D, and this distance from this point to this is lever arm for C2, and this is equal to D minus D dash. So, moment of Mu2, moment of resistance developed by the produced by the compression steel is equal to FSC ASC minus FCC into ASC into D minus D dash. So, total moment of resistance is equal to Mu limiting plus Mu2. Mu limiting, the value is 0.36 FCK BXU D minus 0.42 XU, and Mu2 is FSC into ASC into D minus D dash. So, total moment of resistance Mu limiting is plus Mu2 is this. Now, XU denote the depth of neutral axis, whereas XU max denotes the maximum depth of neutral axis. So, like singly reinforced beam section, in doubly reinforced beam section there are three types of beam section: under reinforced beam section, over reinforced beam section, balanced beam section, balanced or economical beam section. So, first type is balanced beam section. So, in balanced beam section, the section in which tensile steel reaches its yield strain and concrete reaches its failure strain simultaneously is called balanced section. In this section, XU is equal to XU maximum. So, depth of neutral axis is equal to maximum depth of neutral axis. This type of section is called balanced section or economical section. So, in this section the stresses reach its maximum permissible value in tensile zone and in compression zone simultaneously. Second type of beam section is under reinforced beam section. When depth of neutral axis is less than the maximum depth of neutral axis, that type of section is called under reinforced section. The section in which tensile stress reach its yield strain earlier than the concrete reaches the failure strain, that is EC is equal to 0.0035 is called under reinforced section. So, in this section the depth of neutral axis is less than the depth of maximum depth of neutral axis, and percentage of steel is less than limiting value of percentage of steel, and the formula for moment of resistance is used in this in over reinforced beam section m sorry uh, 0.87 Fy Ast into d minus 0.42 xu. Third type of section is over reinforced section. So, the section in which concrete reaches the failure strain earlier than the steel reach its failure strain. So, this type of section is called over reinforced section, and in this section the depth of neutral axis is greater than the maximum depth of neutral axis. So, there are three type of beam section: balance section, under reinforced section, and over reinforced section. Mu limiting, if we want to find the value of limiting value of moment of resistance, we simply put the value of xu max instead of xu. Instead of xu, we put the value of xu max, and then we get the value of limiting moment of resistance. So, limiting value of moment of resistance is equal to 0.36 FCK BXU max into d minus 0.42 XU max. This is the lever arm, and Fs Asc into d minus d dash, where FCK is the characteristics compressive strength of concrete, B is the width of beam, XU max is the maximum depth of neutral axis, D is the effective depth of the beam, FSC is the stress in compression steel, and Asc is the area of compression steel, B is the effective depth, and D dash is the effective cover for compression steel. The value of FSC depend upon the amount of strain in compression steel from the strain diagram. So, the value of strain in compression steel can be calculated from the strain diagram. So, please see the strain diagram. This is the strain diagram. The maximum strain in the outermost concrete fiber is 0.0035. At the compression steel level is the Esc, and this is the depth of neutral axis xu, and this distance is d dash. So, this distance xu minus d dash. So, these are the two similar triangles. From these similar triangle, we get 0.0035 divided by xu is equal to Esc divided by xu minus d dash. So, from strain diagram, 0.0035 divided by xu here, 0.0035 divided by xu is equal to Esc divided by xu minus d. From this we can calculate the value of Esc, and the value of Fsc, stress in compression steel, can be obtained from the stress strain curve for given type of steel. Next is design step for doubly reinforced beam. So, first step is calculate the limiting moment of resistance, Mu limiting value. Here Mu is equal to 0.148 FCK BD square. This limiting value of moment of resistance for Fe250 steel, so or mild steel, and limiting value of moment of resistance is equal to 0.138 FCK BD square is for Fe415 steel, and the limiting value of moment of resistance is equal to 0.133 FCK BD square. This value is for steel Fe500. So, first step, calculate the limiting moment of resistance. Second step, calculate the factored maximum bending moment, and formula for factored maximum bending moment is mu is equal to Wu into L square by 8, where Wu is the total UDL, factored UDL, total factored load, L is the effective span. So, from this formula we calculate the maximum bending moment. Then check mu is greater than mu limiting. So, in third step we check the value of bending moment is check whether the bending moment is greater than mu limiting. If mu is greater than mu limiting, then the beam section is to be designed as the doubly reinforced beam. If mu is greater than mu limiting, then find mu2 is equal to mu minus mu limiting. Fourth step, calculate the area of tensile reinforcement Ast1. Ast1 is equal to mu limiting divided by 0.87 Fy into d minus 0.42 xu max. Mu limiting is the limiting value of moment of resistance. Fy is the characteristic tensile strength of steel. D is the effective depth. Xu max is the maximum depth of neutral axis. So, from this formula we can calculate the value of Ast1. The depth of neutral maximum depth of neutral axis is equal to 0.53 d, where d is the effective depth of the beam. So, Xu max is equal to 0.53 d for Fe250 steel, 0.48 d for Fe415 steel, 0.46 d is for Fe500 steel. So, there are three type of steel, and these are the three value of maximum depth of the neutral axis. Then find the value of Ast2, and Ast2 is equal to mu2 divided by 0.87 Fy d minus d dash. Then add these two, Ast1 plus Ast2, and find out the value of the total area of tensile reinforcement. And from total area of tensile reinforcement, we select the suitable diameter of bar and find the number of bar required. Fifth step is the calculate the area of compression reinforcement Asc, and the compression reinforcement is designated as Asc, and Asc is equal to mu2 divided by Fsc d minus d dash, where Fsc is the stress in compression steel, d is the effective depth, d dash is the effective cover for compression steel. From this area of compression steel, we select the suitable diameter of bar and find out the number of bar required as a compression steel. So, next step is the sixth step, check for shear and design of shear in reinforcement. After when we decide the area of tensile reinforcement or compression reinforcement, then we have to apply the check for shear and design shear reinforcement. In this check, we calculate the shear force and then the nominal shear stress, and we check if the nominal shear stress is greater than the shear strength of the concrete, then there is no need of shear. If the nominal shear stress is greater than the shear strength of the concrete, then there is need of shear reinforcement. If the nominal shear stress is less than the shear strength of the concrete, then there is no need of shear reinforcement. Seventh, check for development length, and this is check for development length. LD is not greater than m1 upon v plus L naught. By this method, we apply the check for development length. Next, check for beam for deflection considerations. So, first one, we calculate the percentage of tensile reinforcement, and it is denoted by PT. PT is equal to 100 Ast upon BD, where Ast is the area of tensile reinforcement. Secondly, we calculate the percentage of compression steel, and it is denoted by PC. PC is equal to 100 Asc upon BD, where Asc is the area of compression steel. Then calculate the value of Fs from this formula. Fs is equal to 0.58 Fy into Ast required, area of tensile reinforcement required, divided by the Ast provided, that we have provided the area of tensile reinforcement. From this formula we calculate the value of Fs. Then find the modification factor Kt, Kc and Kf